Okay, so in this video, we're going to take a look at diagnostic tests. And essentially, diagnostic tests are those tests that are going to help us distinguish between people who have the disease and who don't have the disease, or between a person who does have, or basically help us determine whether a person has the disease or doesn't have the disease. So two ends there. So just to jump into a little bit about when we actually want to prescribe a diagnostic test, right? So I have three possibilities. Let's say a person comes in and I perform an initial test. I'm going to assign them a pre-test probability, and that's essentially the probability that the person actually has the disease. If my pre-test probability after my initial test falls in between 0% and the test threshold, then I'm saying that the probability of the disease is low and that no further testing is warranted, and I can just cross that diagnosis off the list. But the person probably doesn't have the disease. If my pretest probability falls over here between my treatment threshold and my 100% marker, then I'm saying that the probability of the disease is so high that I actually do need to go and treat the disease. I don't need to perform any other sort of diagnostic test in order to confirm this. But more often than not, pretest probabilities fall in between the test threshold and the treatment threshold, such that we're faced with this diagnostic uncertainty, whether the person doesn't have the disease or does have the disease, so that the person has to go and perform an additional diagnostic test in order to ensure that the person either does have the disease so we can cross it off the list, or does have the disease so we can go ahead and treat them, or doesn't have the disease so we can go and cross it off the list. So that additional test is the diagnostic test that we're going to be talking about. So actually, what we're going to start with is talking about how do we go ahead and develop the diagnostic test before we can actually talk about, the whole idea of reduction in uncertainty. So how do we develop a diagnostic test? And first of all, what is the best test, right? Let's say I've developed a test, and my test is either able to move me from the test threshold or below the test threshold or above the treatment threshold, right? But another test is also doing the same thing. Then this falls into a cost minimization problem. Essentially, I want to use the test that is the least expensive and probably also the least invasive, and that will be my best test, right? But before actually considering this whole idea of reductions in uncertainty and how my diagnostic test might go about doing that, let's talk about the whole idea of developing a diagnostic test first, right? And that has to do with actually a diagnostic study design. So let's look at what a diagnostic study design might look like. So I'm just going to go ahead and erase this. Okay, so in my study design, I start with a representative sample, and we'll talk about what constitutes a representative sample for a diagnostic study in a bit. After collecting my representative sample, I'm going to go ahead and perform my test my diagnostic test that I'm trying to develop, and I'm going to, so this is going to happen at time 1, and then I'm going to perform my gold standard test at time 2. Right? And if you remember this is predictive criterion validity, right? That I'm going to be perhaps even measuring. So if you remember, I'm going to be reporting sensitivity, specificity values, and all of that to determine whether or not this test was good if it behaved in its behavior against a gold standard test, right? Okay, so what constitutes a representative sample? So the first thing I want to make sure when I'm choosing patients is that I'm choosing patients consecutively. Like patients come in, I choose, patients come in, and then I choose them. I want to make sure that the patients I'm choosing, however, are representative of the sample, are representative of the patients for whom the diagnosis is uncertain. I don't want to choose people who are normal. I don't want to choose people, so not disease, and I don't want to choose people who do have the disease and need to go through. I want to choose people who I don't know whether or not they have the disease. Otherwise, I'm going to risk something known as spectrum bias. And another idea for spectrum bias is the fact that I'm choosing people perhaps I chose some people from tertiary care settings, right? So it might be reasonable to say that, okay, there's going to be a different proportion of people with the disease in tertiary care setting than are present in a primary care setting. So obviously, if I chose a sample from a tertiary care setting, my test will appear to look better in a tertiary care setting, or appear to work better in a tertiary care setting than in a primary care setting. But that's because I chose people from a tertiary care setting. So we need to be careful where we're getting the patients from and where we're trying to apply our results to, in terms of selection bias and in terms of actually creating that study design. If we chose people from a tertiary care setting, we want to make sure that we apply our results to that tertiary care setting also. Now just to jumble back, so I've chosen a representative sample, but just to jumble back now, I need to go through a couple phases in order to demonstrate the ability of my test to distinguish between disease and non-disease, right? Or event and non-event. And I need to go through basically phase 1 and phase 2 before actually even attempting phase 3. And we'll talk about what phase 3 is also in a bit. But essentially, phase 1 and phase 2 deal with the test's ability to detect a difference between two known groups that are different, right? And if the test is unable to differentiate between people in phase 1 and phase 2, when we actually know who has the disease and who doesn't, then how can we expect our test to actually perform well in a phase 3 or a phase 4 when we don't know what diagnosis the patient has, if the patient has the disease or doesn't have the disease, right? So we want to make sure that our test performs as expected in phase 1 and phase 2 trials. So phase 1 trials are those trials that are trying to ask questions like, do the test results in affected patients differ from those in normal individuals, right? So essentially what happens here, essentially what happens here is that I'm going to collect a known group and then I'm going to perform the test on them. And I'm asking the question here, do the test results in affected patients differ from those that are normal, right? That don't have the condition. In phase 2, what I'm going to do is I'm going to start with a test, and then I'm going to apply it onto the known group. So the test comes first, and then I figure out whether then I figure them out. So the question I'm asking here is: are patients with certain test results more likely to have the target disorder? And if I can show that my phase 1 and 2 studies are both showing promising results, then phase 3 might be warranted, right? But I need to show that my test is working under even the most ideal of conditions, right? And if I do show this, then I still can't make any sort of conclusions, right? I can't say that, oh, the test is ready to be used in usual practice. I need to make sure that the test goes into phase 3, where I can find a representative sample for whom patients or for whom diagnosis is uncertain. So that's when this is coming up. That's why I'm now performing the test against a gold standard, because I know that these two phases have been passed. Okay, so how do I select a gold standard now, right? I've talked about choosing a test, but how do I go ahead and select a gold standard? Well, a gold standard is essentially something that is very valid, something that is very reliable, basically shown by evidence to be something that is able to actually distinguish between patients with a target condition and without a target condition. So something like an MRI, for example, is a very good example of a gold standard, right? Okay, so now we can jump into something like about detection and performance bias. So we already talked about spectrum bias, the idea about how if you chose from a primary care setting or a tertiary care setting, then the results might be different, vice versa, right? That's spectrum bias. That's a type of selection bias, right? That my results from a tertiary care setting might not apply to a primary care setting, and my results from a primary care setting might not apply to a tertiary care setting. Well, again, we want to make sure that there's some blinding happening to prevent some sort of detection or performance bias, right? We want to make sure that there are two different people, that the person performing the test is different from the person performing the gold standard test, and that they're blind to each other's results. The person doing the test doesn't know the gold standard, and considering that we're not doing them at the same time, they won't know anyways, but that the person performing the gold standard doesn't know what results the test got. Otherwise, it might influence the person performing the gold standard to perhaps report something that wasn't there or was biased in some way, right? So if we didn't have bias happening, we might actually introduce verification bias. And verification bias is a type of performance bias, which essentially influences the choice of reference standard. So it influences the gold standard testers testers' decision to perform the gold standard, right? And they essentially might then not choose to perform a gold standard, or will choose to perform a gold standard depending on the test results, if they knew it or didn't know it. So obviously we want both people to be appropriately skilled. You want to make sure that they're two different people and that they're blinded to each other's results. But you want to make sure that whichever comes first, the test or the gold standard, that the result of that test, whichever one came first, doesn't influence the decision to perform the next test. You could also potentially overestimate the performance of your test by leaving out complex cases. So if you leave out the complex cases, your test might overperform, because we're not even testing its ability to differentiate between the complex cases, right? So we want to make sure that it does all of that stuff in order to make sure that your test is, in order to make sure that you have a valid sort of study design going on right there. So now, how do I ensure that my test is valid? I've chosen a test and I'm doing the test. I've chosen a gold standard. I've determined, I've tried to minimize a sort of performance bias. I've taken into account selection bias, right? How do I go about actually performing the test and making sure that the test is valid? Well, that brings us down to a couple of calculations. And I'll have a lot of examples, or I'll have a couple examples of each calculation in the description. We're just going to go over the general definitions of each of these, and you can read the description, or the description basically in the YouTube bar at the bottom. So, typical summary measures that help us determine the effectiveness of the test include sensitivity. We have specificity. We're going to have positive predictive value, negative predictive value, a likelihood ratio, which can be a positive likelihood ratio, or it can be a negative likelihood ratio. And we can use receiver operating characteristic curves and area under the curve to determine all of this, right? Now, I'm probably not going to go over all the calculations, especially for sensitivity, specificity, positive predictive value, negative predictive value. I'll go over the definitions, but these are essentially very simple calculations that I'll have examples of in the description below. So let's start with sensitivity. Oh, and I guess what we should mention first is that we're using 2x2 contingency tables to determine whether or not, to determine these values, essentially. So let's say that our gold standard is up here, and let's say that we have our test down here, right? So our 2x2 contingency table is going to go like this: positive, negative, positive, negative. Let me erase this, and then we'll draw a better 2x2 contingency table, and maybe we'll go through some examples. Okay, so we have our gold standard results up here, and we're going to have our test results down here. Positive, negative, my bad. We should call this positive down here, so we can have a positive here and we can have a negative here. Alrighty, so this here is going to be a true positive, right? Because my test has detected a positive detected by my gold standard. So I'm going to take whatever my gold standard says as truth. So everyone in here definitely has the disease. Everyone here definitely doesn't have the disease. So considering this, these people don't have the disease. This row represents people who don't have the disease, but my test said it's positive. Well, then I've concluded that this is a false positive, right? This is a true negative. My gold standard says it's not, there's no people with disease here. My test also says that. and this here is a false negative. These people definitely have the disease, but my test said they don't have the disease. Okay, and we're going to rely on a 2x2 contingency table to help us determine some of these values for sensitivity, specificity, and all of those values. Okay, so sensitivity. Sensitivity is the proportion of patients who have the target disorder, right? The proportion of patients who definitely have the target disorder and had a positive test result. Okay, so sensitivity is calculated by taking the true positives, dividing it by the proportion of people who did, or the amount of people who truly had the disease. So true positives plus false negatives, right? So again, the sensitivity is the proportion of people who have the disease and who had a test and who tested positive. This is going to be my sensitivity value. Okay. Something we want to take a look at now is an acronym. It's called SNOUT. I should actually not write it like that. It's called SNOUT. And what SNOUT means is that if a test has high sensitivity, then a negative test can rule the disorder out. But there's a better way to look at this, right? Basically what this is saying is, let's say that I have a test that has high sensitivity. Let's say I had a test that has 95% sensitivity, right? Well, if my test has 95% sensitivity, then I have very good sensitivity. And let's say then I got a negative test result, okay? Then I can be pretty sure that the person who got the negative test result doesn't have the disease. That's what SNOUT is saying for a test that has high sensitivity value. But you can think of it this way. If I have high sensitivity, right? If I have high sensitivity values, then I have low 1 minus sensitivity values, right? If I have 95% sensitivity, then I only have 5% 1 minus sensitivity. Well, sensitivity is the rate of true positives, right? 1 minus sensitivity is the rate of false negatives, right? So if I have high sensitivity, my rate of false negatives is going to be low. So every time I get a negative, I can be pretty certain that this person really is negative because my rate of false negatives is low. Okay? So that's the idea behind sensitivity. We can look at something very similar for specificity. Just gotta erase this quickly. Specificity is calculated by taking, specificity, first of all, is the proportion of patients who do not have the target disorder and who tested negative, right? So specificity is the true negative rate. We're going to take the true negatives and we're going to divide them by true negatives plus the false positives. The proportion of people who do not have the target disorder, right, and who tested negative. Now, if a test has high specificity, we're going to look at something called spin. Basically, what this is saying is that if a test has high specificity, a positive result is going to rule the disease in, right? And the result, and basically, let's say we have 95% specificity. That means we have 5% 1 minus specificity. Let's just take a look at it in this way. If you want to actually understand and not memorize the acronym, then we can take a look at it like that. So if I have high specificity, right, 95% specificity, then I have a high true negative rate. But that means I have a low 1 minus specificity rate, meaning that I have a low false positive rate, right? So now everybody who comes in, right, and with a test that has 95% specificity, so very high, everybody who comes in and gets a positive result, I can be very sure that it's probably not a false positive because I have very low false positive rate, right? So I can be pretty sure that that person does have the disease. So I rule the disease in. And that's what spin is telling us. Okay? So now we've discussed sensitivity and specificity, and something we want to distinguish between first is the idea of parametric and non-parametric statistics. Sometimes what a paper will do is report, or actually let's consider this first, that sensitivity and specificity both have values that range from 0 to 1, or from 0% to 100%, right? Now, if your confidence interval values, and if they report confidence interval values that actually fall outside of 0% or 100%, it means that they haven't used the correct statistics to calculate the confidence intervals. The correct statistics here would have to be non-parametric statistics, and instead what they've done is they've used parametric statistics. Sometimes if your sample size is large enough, you could potentially use parametric statistics because then you'll be able to fall between the confidence intervals. But essentially, the reason why you don't want to use parametric statistics sometimes is because they make assumptions about your population. For example, that it follows a normal distribution, right? So you want to make sure that they're reporting maybe non-parametric statistics. So that's the whole idea of sensitivity and specificity. If I have good specificity, if I have good sensitivity values, after comparing with my gold standard and my test, then I can say that, okay, I have a very good test going on here. Well, that brings us to the idea of positive predictive value and negative predictive value. So positive predictive value is essentially just the proportion of patients who have a positive test who actually have the disorder. Okay? So we're going to take the true positives, and this time we're going to divide it by true positive plus false positive. Alrighty? The proportion of people who have a positive test result and who tested positive. And negative predictive value is the proportion of people with a negative test result and who tested negative. So true negative divided by true negative plus false negative. The proportion of people who tested negative and who actually, or the proportion, yeah, and who actually don't have the target disorder. Okay, so that's the whole idea between or behind true negative value, positive predictive value and negative predictive value. Alright, so let's erase this. And now we can get into a discussion about likelihood ratios. So sometimes a clinician is going to, well, a lot of the times, a clinician is going to want to know the odds of actually having the disease, given that you have a positive test or a negative test. And we can use likelihood ratios to tell us that odds. A likelihood ratio positive, or an LR positive value, is going to tell us the odds of having the disease given that a person has the positive test compared to someone who doesn't have a positive test. Okay? So the way we calculate LR positive values is we take sensitivity and we're going to divide it by 1 minus specificity. Alright? Take sensitivity and you divide it by 1 minus specificity. And this is going to give us the odds of having the disease given that I have a positive test compared to someone who has a negative test or didn't get the positive test. LR negative values, on the other hand, are calculated by taking 1 minus sensitivity divided by specificity. And this LR negative tells me the odds of having the disease given that I have a negative test compared to someone who has a positive test, right? So you might then wonder that if I have an LR, since an LR is clearly an odds ratio, if I have a likelihood ratio of 1, then what that tells me is that there's no difference, right? It means it's not effective at moving the uncertainty at all. Okay? So likelihood ratios are going to tell us about the effectiveness of moving the uncertainty from the middle to either past the test threshold or behind the treatment, past the treatment threshold and behind the test threshold, right? So I'll put an example of this in the bottom, but we're still going to use contingency tables, right? Sensitivity, we calculate our sensitivity, and we're just going to calculate our specificity, and then we're going to do 1 minus that. Okay, there are shortcuts to do this, and I'll also include those in the description at the bottom, right? Now, what's important to know is how do I know whether or not I could calculate a test, and how do I know whether or not this test is going to move me past the test threshold or move me past the treatment threshold? Well, there are values for test thresholds. There are values for LR positive and LR negative that tell us the effect that they have on diagnostic certainty. So let's just go ahead and erase these. Okay, so for LR positives, if I have an LR positive value that is greater than 10, then I am sure that there is a large and conclusive effect on certainty. I can be very sure that it'll either move me past the treatment threshold or it'll move me behind the test threshold. If I have an LR positive of between 5 to 10, then I have a pretty moderate effect on my certainty. If I have an LR positive value of 2 to 5, then I have a small, but it's still somewhat important effect on my certainty. And if I have a value of LR positive between 1 and 2, then I have a small and rarely important. Remember, 1 is that idea, an LR of 1 means that there's no difference, right? It's not going to move us, it's not going to move our uncertainty at all. For LR negatives, right, we want them to be smaller. So we want our LR positives to be greater, right? If a person has a positive test, we want the odds of them to have the disease to be greater. But if a person has a negative test, right, we want the odds of them to have the disease to be low. So if your LR negative value is less than 0.1, then again, you've had a large and conclusive effect. If you have 0.1 to 0.2, moderate effect on certainty. 0.2 to 0.5, you have a small but somewhat important effect on your certainty. And 0.5 to 1, well, that's a small and rarely important effect on your certainty. Again, there's that 1 again, right? Now, there's the idea of not having a 2x2 contingency table, right? You might have for your test results, and let me just erase this and show you. This is something that you might want to remember because the LR positive and the LR negative values will tell us the effect that they have on moving us from moving our uncertainty, right? And we'll talk about how we can actually go ahead and find a post-test probability using that likelihood ratio. But the first thing I want to talk about is, well, what happens if my 2x2 contingency table is no longer a 2x2 contingency table and my results are a lot more complex, right? So what if I have something that looks like this? So I still have my gold standard, right? And I still know that I have positive and negative, right? So either that there's something present and there's something not present, right? And let's say that I have my test here, right? But I'm measuring for a whole bunch of different things. Like I'm measuring for, let's say, some sort of a large disease state. Then I'm looking for some sort of small disease state. Then I'm looking for some sort of moderate disease state, right? But it's no longer a contingency table. And I should put a normal disease state, right? It's no longer a 2x2 contingency table. So I'm going to have values, and I'm going to put A, B, C, D. We're going to put E, F, G, and H. Right? I'm going to have values here. How do I go about and calculate my sensitivity and specificity values here now? All right? What do I do? Well, it's actually pretty simple. In order to calculate sensitivity, just recall the definition of sensitivity. Sensitivity is, and let's say I'm trying to calculate the sensitivity for this part right here, right? Or actually not, that's not really that important. But sensitivity is essentially the proportion of patients who have the target disorder and who have a positive test result, right? So these are people who might have positive test results. For large, it might be this. For small, it might be this, right? So I want to calculate my sensitivity values for that. And let's say I have a total here. And let's call this X and Y. So in order to calculate my sensitivity from a table that looks like this, I have to say, okay, I'm looking for my sensitivity for large now, okay? For people who have a large disease state. Well, sensitivity, again, is the proportion of people who have the target disorder, right? So in my denominator for my sensitivity, I'm going to have X. And people are with, so the proportion of people with the target disorder who have a positive test result, so A, right? So really what I'm doing is I'm doing A over B plus C plus D of all the people who don't have the positive test result for this, but still have the disease, or still have the target disorder. That's how I'll calculate my sensitivity for this, right? Now let's say I wanted to calculate my specificity for this, right? Well, all you do is you take, well, first of all, specificity is the proportion of people who don't have the target disorder. So all of these people, right? So we're going to put Y, and who actually had a negative test. So if I wanted it for small, then I would put F. If I wanted it for large, then I would put E up here. So E over Y is going to give me my specificity for this, right? And then I could potentially go ahead and calculate my likelihood ratio, right? I could just do sensitivity divided by 1 minus the specificity value for large. And then I'll have my LR positive for this, right? Or my likelihood ratio for this. And that would be my LR positive, right? But there's a shortcut, right? What if I don't want to go through the whole what if I don't want to go through the whole thing of calculating my sensitivity values and calculating my specificity values and then putting it in my calculator and saying, okay, sensitivity divided by 1 minus this, right? You could take this through a whole, you could basically you could prevent yourself from doing this, putting this whole thing in your calculator. What you could do, and this is a shortcut only for likelihood ratios. For specificity, you do have to calculate this. For sensitivity, you do have to calculate this. But the reason why it differs for, okay, let me just erase this, and I'll just put T up here. So this is the test. The reason why it's different is because we know that LR positive is sensitivity divided by 1 minus specificity, right? Well, 1 minus e to the y, and this section here is really just f over y, right? It's really just f over y. So I'm going to calculate, and actually I think I might have said something wrong here, because specificity is the amount of people who don't have the target disorder. So really what I should have said, not e over y, it should have been actually, it should have been f plus g plus h over y. F plus g plus h over y, right? It's the amount of people who don't have the target disorder, the proportion of people who don't have the target disorder and who have a negative test result. So it's all of these people, right? So I said that wrong. I'm really sorry about that. So again, I'll go back to this idea of the shortcut. This is my specificity. I need to do this to calculate my specificity. I need to do this to calculate my sensitivity. But what if I don't want to go through the trouble of taking this, calculating this first, calculating this second, and then doing sensitivity, and then dividing it by 1 minus this, right? Well, f 1 minus f plus g plus h divided by y is really the same thing as just doing e over y, right? Right? I'm taking from 100 all of this, meaning I'm really just going to be left with this at the end of the day, e over y. So this is the same thing. Taking this, dividing by this is the same thing as taking 1 minus this divided by this, right? So what I could do is, when I'm trying to calculate my LR positive value, instead of going to do something like this, whoops, a divided by x divided by 1 minus f plus g plus h divided by y, I could instead just do a divided by x, right, and divided by e over y, right, because this is equivalent to this. Okay, so that's just the simple, shorter way to do this. Yeah, ignore my other mistake there. And the reason why this, once more, is, in case I mess up the explanation, the reason why this is specificity is because specificity is the proportion of people who don't have the target disorder and who tested negative. So the specificity for this value, for large, would be F plus G plus H divided by Y. Right? So that is specificity. Or that is basically having a more complicated version of the 2x2 contingency table, and how we could go about calculating sensitivity, specificity, and potentially likelihood ratios on this kind of table. Alrighty. Now, like I said, our likelihood ratios are going to help us calculate some sort of post-test probability, right? So let's say that I'm just going to go through a quick example. There will be an example calculation at the bottom. Let's say that I had a pretest probability given to me as 40%. Okay, so I don't know whether or not the person had the disease. My pretest probability is 40%. Okay, so, and I have a likelihood ratio. Let's say my LR, my likelihood ratio is 11. Right, so I have a pretty good likelihood ratio. It is going to move, it has a large and conclusive effect on my certainty, right? But I want to know what my post-test probability is. The problem here is that I can't multiply a probability by an odds, so I need to convert my probability into an odd. And the way that I do that is 40%. I'm just going to divide it by whatever is remaining in that 100. So 100 minus 40 is 60, so I need to do 40 divided by 60, and 40 divided by 60 is about 0.67, right? So that is my pre-test odds. And then I can multiply with my likelihood ratio. So 0.67 times 11, and that should give me around 7.3-ish, or 7.3-ish, just doing this off the back of my head right now. But it should give me around 7.3, right? And then I want to convert this, now my post-test odds, into a post-test probability. And the way that I do this is I take my post-test odds and I divide it by my post-test odds plus 1. So that should be around, let's say, 0.9-ish, 0.9, right? Might actually be a little less than that, so maybe let's say 0.88. And that'll be about 88%. So my post-test probability is now 80%, right? My diagnostic uncertainty went from 40%, and now I've moved to 88%. And if my treatment threshold was, let's say, 85%, right? If this was my treatment threshold and this was my 100% bar, well, I'm in here now, right? So it's moved me into this range, and therefore I can say, okay, this person has the disease, I'm going to go treat them. If it moved me to maybe 82%, right? If it moved me to 82%, then I'd be here and I'd still be uncertain. Okay, but considering that it moved me here, and considering that it moved me here, I might actually want to recommend treatment if this was my treatment threshold. So that's just a short way of actually doing some sort of calculation of moving from a pretest probability and a likelihoods ratio to a post-test probability to determine whether or not we should move on with disease or cross the diagnosis off the list. I'll have a lot more examples of this, or a couple more examples of this in the description later on. Okay, and the final thing we want to take a look at is receiver operating characteristic curves. So ROC curves, and we want to look at area under the curve. But before we take a look at any of these, let's take a look at the different types of scenarios we can get for classifying. So tests can be drawn on classifier curves. I just made that name up. It might not be called classifier curves, but I like to call them classifier curves. And we can have a couple of different scenarios. So we can have a scenario that looks like this. So test. We could have a scenario that looks like this. And you might be wondering what these are. I'll explain it in just a second. And we might have a scenario that looks like this. So the idea here is that we want to establish essentially a cutoff point, right? want to know at what point do I cut off so that I'll have the fewest errors in terms of recommending some sort of intervention. So this test here and everything on this side, everything on the left graph here, is going to be my true negatives, and everything here is going to be my true positives. Okay, so here I can be pretty certain that this is a good cutoff, right? My test is definitely going to give me true positives on this side, and this side my test is definitely going to give me true true positives, right? If I have a test that looks like this, well, this is not a very good test, right? Not a very good classifier. I would probably not want to use this test at all, considering the fact that even if I found a good cutoff point, I'd probably not be able to minimize my false positives or maximize my true positives, right? This is something that we're faced with more often in real life. So I'm gonna make that graph a little bit bigger. Okay, so oops, let me just draw that graph a little bit bigger. So this is something that we're faced with more often in real life, right? As you can see, this curve represents all the people that are truly negative. This curve represents all the people that are truly positive. But they're crossing, right? And I want to find out, well, where is the perfect cutoff point? You know, at what point am I going to minimize false positives and at what point am I going to maximize true positives, right? Because as soon as this curve got into this range, right, these people are truly negative, but this range is, right, let's say my cutoff value is here. Well, everything to the right of this is this graph's boundary. This graph represents the true positive people, right? So all of a sudden, the people who were in this graph, some of them are right here, right? Well, now I have some rate of false positives. These people don't actually have the disease, but they're going to be picked up as though they are because of my cutoff point, right? So I might not want to put my line there because maybe minimizing false positives is something that I'm more interested in. So maybe I'll put my cutoff here. Whoops, let me put that back. Not exactly sure. Oh, there we go. So yeah, maybe I want to minimize my false positives. So I'm going to put it here, right? So now I can be 100% certain that I'm not going to get any people, because anything to the right is true positive. So now I can be 100% sure that all of the people that are truly negative are definitely going to be truly negative. But everything to the left of this line, right, is negative. These people are positive, right? So suddenly I've lost some of these truly positive people. And as a result, what I've done is that at the cost of minimizing my false positive rate, I've decreased my true positive rate, right? I've decreased my true positive rate. At the cost of increasing my true positive rate, right? If my boundary is here, everybody that actually was diseased is definitely going to be included. So at the cost of maximizing my true positive rate, I've also somewhat increased my false positive rate. So we're trying to find the best cutoff value, right? Where on this graph can I find the best cutoff value? That will help me maximize my true positives and minimize my false positive rates, right? And sometimes it just comes down to whether or not clinicians, it's more important to clinicians to minimize false positives or maximize true positives, right? But we can actually use something called a receiver operating characteristic curve to help us decide on where the heck we're going to put that cutoff point, right? So I'm going to draw that graph back here. So we might actually refer to it. I'm going to draw that graph back here. Just remember the two cutoff points. So we had this cutoff point and we had this cutoff point. All right. Our receiver operating characteristic curves looks like this. Okay, and we're going to have a line like this. And let's just say we have a couple of different tests. So we have black line, that's probably going to go like this. And let's say we have another test that looks like this. Okay, and on the y-axis, I'm going to plot the rate of true positives. Whoops, that didn't work out very well. Just, I've plotted the rate of true positives on this line. And on the x-axis, I've plotted the rate of false positives. Okay, now, before deciding cutoffs, which test do you think is the best test here? The worst test is definitely this test, right? And the best test is this test. And the idea here is that if a point comes close to the upper left-hand corner, the point or the curve that is closest to the point to the upper left-hand corner, that is the best test, right? And this is reflected in the area under the curve, right? It's literally this area. Okay, the more of the box that we can fill under our curve, the better our test is going to be. The better our test is at explaining or correctly identifying whether patients have changed or not, whether patients have the disease or not, then chance. That's better than chance, right? So something that has an area under the curve of, let's say, more than 0.5, or let's say something that has an area under the curve of 1. So that means somehow the point is up here, right? That is a perfect classifier. That test does much, much better than chance in correctly identifying patients who have changed or not. It is a perfect test. At the same time, if a test comes down here, right, and it has an area under the curve of 0, it's also a perfect test, right? It just means that we can flip the results. Maybe patients who did have the disease actually don't have the disease, and patients who were identified as not having the disease, patients who were identified as having the disease didn't have the disease. So area under the curve of 1, area under the curve of 0 represent perfect tests. An area under the curve of 0.5, which would be something like this line right here. Well, an area under the curve of 0.5 means that the test is no better than chance at classifying people who have the disease and who don't have the disease. The closer we are to that upper left-hand corner, perhaps to the lower right-hand boundary, the better our test is going to be, right? Now we can talk about cutoff values. So let's say that our test, this graph here, is represented by this test. I'm going to erase all the other lines. Not that important to me, these other lines, now that we've discussed them. Let's say this is the curve that my test is going to be represented by in this graph, right? Well, this is ideally the point that I want. It is the closest to the upper left-hand corner, and it's going to maximize my area under the curve, right? So that's the point that I want, and it may fall somewhere in here, right? But what you might notice is that, let's say it was important to me that I wanted to somehow increase the rate of my true positives. So I need to pick a cutoff, right? To increase the rate of my true positives, I need this to be my cutoff line, right? Because I want everybody represented by this curve to be on the right side of this line. So this is my cutoff now. Well, what I've done by increasing the rate of my true positives, as you can see, right? Let's say as I moved my cutoff to this end, I've moved my true positive rate here. I've actually maximized my rate of true positives here, right? So I've maximized it. I'm actually at the upper boundary here now, right? And the reason I say I've maximized it is because everybody who's reflected by this graph is actually on the right side of this line. So I've maximized my true positive. But you can see that I've maximized them, even though I've maximized them, I've actually increased my false positive rate, right? So I've maximized my true positive rate at the expense of increasing my false positive rate. Now let's say I wanted to decrease my false negative rates. Decrease my false positive rate. So everybody represented by this curve needs to be on the left side of this line, right? Well, if I move the cutoff to this end, right here, then my values fall here. And I've clearly completely minimized my false positive rates, as you can see. So I'm down here now. False positive rates are minimized, right? So I am somewhere the line should be going like this, right? So ignore that this is, So I've minimized my false positive rates, but you can see that I've done that at the expense of also decreasing my true positive rates. So it comes down to which one is more important to clinicians, maximizing true positives or minimizing false positives, or is there a balance between the two that we're willing to accept and find the best cutoff for, so that we can have a good test, and could be comfortable with that. Okay, so that's the whole idea of receiver operating characteristic curves, and how a test is good, and determining which test is good and which test might not be as good, right? Okay, so now we need to identify how do we go about calculating sample size. Well, the only way that I know how to calculate sample size for diagnostic tests is for parameters. So, for example, what I mean by that is if I'm trying to estimate, for example, sensitivity, specificity, negative predictive values, positive predictive values, likelihood ratios, and so on and so forth, if I'm trying to estimate those type of parameters, then I need to calculate sample size a certain way. And that's what I'm going to show you. If you're trying to statistically compare two tests, so for example, you're trying to compare the specificity of one test with the specificity of another test, well, then you're going to need to calculate sample size a completely different way. So we're going to consider the sample size calculation for estimating a parameter. And considering that we're estimating a parameter, we don't need to worry about any sort of power, right? Because we're not worried about detecting the difference between two groups right now. We're just worried about estimating the sensitivity, perhaps specificity, some sort of parameter, right? So the way that we calculate sample size for perhaps sensitivity and specificity is we're going to, because there's two different equations, so I'm going to write the equations down. So Z alpha over 2 squared times the sensitivity times 1 minus sensitivity divided by D squared times prevalence. And I'll explain what D squared is in a bit. And then sample size for specificity is similar, Z alpha over 2 squared times specificity times 1 minus specificity, and we're going to divide that by D squared times 1 minus prevalence. Okay, and you might then be asking, well, which sample size calculation do I use, right? So you want to first identify which one is more important to you, right? Is your sensitivity more important? Is it more important to you to have a good true positive rate, or is your specificity more important? Is it more important to you to have a good true negative rate, right? And for whichever one is more important to you, right? For example, if it's important to me to reduce my rate of false negatives, then it's important to me that I increase my sensitivity, right? If it's important to me that I want to reduce my rates of false positives, then it's important to me that I increase my specificity, right? So what I want to make sure is I'm going to basically calculate my sample size based on whatever is most important to me, right? So if I want to increase my sensitivity value, then I want to calculate my sample size based on sensitivity, obviously. But since I want an estimate, now that would be usually what you want to do. But since you want an estimate for both parameters, right? You usually want an estimate for both parameters in most studies. What you want to do is you want to calculate the sample size for actually both of them. The first is actually what a lot of studies usually do, and what more people might be doing in critical appraisals. But what you actually want to do is calculate the sample size for both sensitivity and specificity, right? Because you want to be powered to detect both sensitivity and specificity, you're going to use the sample size, whichever one, you're going to use the bigger sample size. So if your specificity gave you a bigger sample size than sensitivity, you're going to go with the specificity sample size, even though perhaps, let's say, sensitivity was more important to you, right? And that's because that will not only power you to detect specificity, but it'll also power you to detect sensitivity, right? Sensitivity needed less people, right? And specificity needed more people. The more people I have, right, I'm going to be able to detect specificity and sensitivity now. So that's why I want to use my sample size based on the greatest sample size, depending on which spat out the greater sample size. But obviously, if my sensitivity is more important to me, so if it's more important to me that I'm reducing my rate of false negatives, then I want to make sure that I increase my sensitivity, right? And if it's more important to me that I decrease my rate of false positives, then I want to increase my specificity. What some people might do is calculate sample size based on what's more important to them, but it's really more precise or more correct to calculate sample size based on whichever number is bigger. And that is basically it for diagnostic studies. We're going to quickly talk about, before ending the module, we're going to quickly talk about well, how do we actually move into different phases? So now we've perhaps performed, or now we've developed a tool, right? We've developed a diagnostic tool, and let's say that it's a good diagnostic tool. So I've proven that it has good sensitivity and good specificity values. Well, how do I go about maybe using it in some sort of phase 3 or phase 4 settings? And this goes into the idea of screening, right? And this goes into the idea of screening and whether or not screening is warranted, right? And we'll talk about whether or not screening is warranted in a bit, but let's just quickly talk about what screening is, right? So I've developed my diagnostic test, and now I want to make sure, now I'm going to use it to screen people. So what is screening? Okay, so screening is basically going to be some sort of intervention, right? And it's going to be basically there to help me detect some sort of diagnosis before the clinical diagnosis actually happens. So this is the difference between early diagnosis, and early diagnosis occurs because of screening, and clinical diagnosis occurs because the person goes ahead and goes to look for help, right? That patient has started to experience symptoms and so on and so forth. So what I do to perform screening, perform a study design, is I get a representative sample, right? I get a sample of people who are disease-free but are still at risk of disease, right? They have certain factors for the disease. And keep in mind that I've now developed my diagnostic test. So my diagnostic test is going to be my screening here, right? And I'm going to take them through, some of them are going to go through a screening test, and some of them are not going to go through screening, right? And I want to see whether or not screening actually improves some sort of outcome. Or perhaps not an outcome, but helps me detect it, helps me detect some sort of outcome, and might actually benefit the patient in terms of some sort of clinical outcome, right? So my screening test is going to be my diagnostic test. It is going to show me whether or not perhaps that the patient has the disease or doesn't have the disease, right? But the first thing we need to consider is, when is screening possible, right? And when will people who are screened actually have some sort of better outcome? Well, now we have some sort of critical point values. So here we have the biologic onset of the disease. So this is when the disease actually started to occur in the patient, right? At this point, we'll say that early diagnosis is possible. So at this point, we could potentially screen, okay? At this point, we're going to say, this is when the usual clinical diagnosis happens. This is when the symptoms start appearing. And at this point, this is when they start to experience the outcome. It could be potentially death, right? It could be some sort of disability, so on and so forth, right? And I also have critical points. So I could have a critical point here, and we're going to call these critical point 1. I could have a critical point here. I'll call this critical point 2. And I could have a critical point here, and this is called critical point 3. And these critical points are essentially just places that I could put a screening program into, okay? So again, what I'm looking for is, if I perform that early diagnosis, is it going to improve some sort of outcome? will people who are screened have a better outcome? Well, if you're able to basically find people who are screened and they actually have a favorable outcome than those who are not screened, that's going to help us determine whether or not we should screen, right? But that favorable outcome, right, is only possible if the person falls into a specific critical point. Let's say that the person falls into this critical point, right? This is the critical point of the disease. This is perhaps when the outcome occurs, or perhaps when something that helps us detect some sort of diagnosis occurs. Well, at this point it's useless because early diagnosis is not possible at this point either, and neither is usual clinical diagnosis. So critical point 1 is not going to help us get screened people have a better outcome. Critical point 3, well, early diagnosis, it's too late for early diagnosis, and it's already after clinical diagnosis. So this is kind of useless too, right? This critical point is not going to help us get people who are screened to have a better outcome. Critical point 2 is what we're concerned with, right? At this point, early diagnosis is still possible, right? If we can identify people here as early as possible that have the disease, then perhaps they can have a better outcome. Okay, so we want patients to be at critical point 2, and this is basically the point at which we can say, okay, screening patients or screened patients might actually have a chance at getting some sort of better outcome than people who are receiving usual clinical diagnosis. But there are 2 problems with screening, and those are types of biases. Okay, so we have lead time bias and length time bias. And lead time bias is what we're going to start with, right? And lead time bias, and let's say that this is where usual clinical diagnosis happens, and this is where my early diagnosis is happening. This is where my diagnostic test is happening. Well, usual clinical diagnosis happens here, right? So I've detected that the person has the disease, and I'm following them to the outcome, and this is when the outcome has happened, right? So it looks like they've survived this long. Well, for early diagnosis, I've diagnosed them at this point. This is when usual diagnosis is happening, and this is where the outcome happened. So now it looks like they've survived longer. But really, the only thing that's happened is that we were just able to screen them a lot quicker, right? It looks like they've survived longer, but really we just started counting their years of survival sooner because we actually gave them a diagnosis sooner. Okay, so that's a lead time bias that happens in a lot of the screening settings. And the next one is length time bias. And essentially length time bias is something that is similar to this, but it's a type of selection bias. And the idea with length time bias is that people who actually have a more aggressive disease, people who have a disease that they're going to move a lot more quickly through, are less likely to participate in any sort of screening program. But they're going to be picked up through that usual clinical diagnosis. And people who don't have as aggressive of a disease are probably going to go for that early diagnosis screening. So they'll look like they've survived longer, right? And the people who have a more aggressive disease will look like they've survived a shorter period of time than those people who elected to participate, who actually agreed to participate in a screening program. So that's length time bias. So all in all, screening is warranted when your test has been proven to go through phase 1, when your test has been proven to go through phase 2, when your test has gone through phase 3 also, right? When your test has gone through phase 3, right? And phase 3 trials ask questions like, are the test results or do the test results distinguish patients with and without the target disorder among those whom we can actually sense or suspect some sort of disorder? So this might have been, for example, an example of when we were developing our diagnostic tests, right? But without the gold standard, obviously, and then compare it to potentially a gold standard. So if it's gone through phase 3, and if it's been able to distinguish between people who do and don't have the disorder, then we move it on to phase 4. right? And phase 4 studies are going to ask, do patients who actually undergo the diagnostic test, do they have some sort of better clinical outcomes than people who don't undergo that screening program? Are they benefited in some sort of, do they benefit in survival? Does their quality of life somehow increase? Or does their quality of life somehow become better? Do they receive some sort of additional function, right? So once it's gone through phase 1, 2, 3, and 4, then we can say, okay, screening is definitely warranted. Okay? So that's the idea of diagnostic tests and when we should go ahead and perhaps, and how we can develop a diagnostic test and how we can evaluate the validity and evaluate how good a diagnostic test is compared to an existing gold standard, and when screening is actually warranted and how we can use our diagnostic test to go through some sort of screening program. Hope that helps.